My aim in this video is to warm you up for our upcoming in-person meeting. I'd like to discuss a simple model of the competition for resources that might occur among consumers like this American goldfinch. I'd also like to simulate that model to generate some qualitative predictions about the evolution of a consumer phenotype. Let's start by discussing the resource that our consumers might exploit. We'll suppose that the resource is a food item that varies continuously in size. To keep things concrete, let's say we're talking about the seeds that are consumed by some birds. We'll assume that the abundance of seeds of a particular size determines the carrying capacity of the population of birds that consumes them. In particular, we'll say that the population of birds that focuses on eating seeds of size X will have carrying capacity K of X, where the graph of K of X looks something like this. What I'm trying to show here is a bell-shaped curve that's symmetric with a peak at 0. In this case, 0 also represents a rescaled mean size. The idea is that the population of birds that targets more abundant resources will have a larger carrying capacity. It would seem advisable then for any given bird to target resources of mean size, since this resource supports the largest number of individuals. However, if it's good for one bird to target the most abundant resource, then other birds will probably want to do the same. So, any bird that sets its sights on size 0 will likely face a lot of competition. This raises an interesting question. How might these opposing tensions come into balance? More specifically, how might the evolutionary process shape a bird's tendencies in a way that balances the benefits of resource abundance against the costs of increased competition? What pattern or patterns might we expect to see? Before we can answer these questions, we'll need to model competition. We turn our attention there now. We've said that birds target seeds of a particular size X, but that doesn't mean that they can't consume seeds of other sizes. Let's suppose that a bird who targets seeds of size X can still consume seeds of other sizes, but that it does so with reduced efficiency. For example, it could be that targeting seeds of size X requires a particular kind of bill morphology that makes it more difficult, but not impossible, to target seeds of other sizes. With this in mind, we expect birds who target seeds of one size to exert some competitive pressure on those who target seeds of a different size, and vice versa. To capture these ideas, we introduce the coefficient alpha as a means of quantifying the competitive effects birds who target seeds of one size have on those birds who target seeds of a different size. I'll use another function here to represent alpha. To understand that function, we'll fix attention on a population of birds targeting seeds of a particular size, let's say size 1. And we'll let the competitive pressure that this population exerts on others fall off in a bell-shaped manner, as shown here by a red curve. With this model, the farther away two competitors' targets are, the less competitive pressure they exert on one another. Importantly, we'll adjust the width of alpha. It might be broad, as shown here, or it might be quite narrow, as shown here. Loosely speaking, the width of the curve will reflect the niche breadth of the population that targets a seed of a given size. So now we have a model for the distribution of resources, and we understand how that distribution affects carrying capacity. We also have a model for competition between birds who target different resources, and so we're ready to generate some predictions. As I said earlier, we'll explore the model by simulating. If you're interested in seeing the details of the simulation, I'll provide a link to the simulation itself and simple instructions on how to run it. In any event, the simulation tracks the distribution of consumer phenotypes, here we're talking about bill size, over time. For simplicity, we assume consumers are asexual. Populations with different bill sizes grow logistically. Variation in bill size is acted upon by selection then, as different populations grow at different rates. New variation is pumped into the system by allowing mutations of small effect to occur when individuals reproduce. In the end, the simulation spits out a picture that looks something like this. The distribution in gray shows the phenotypic variation present after 1,000 time steps. The dashed curve over here shows where things started off. In this case, we can see that the final gray distribution of phenotypes tends to target the most abundant resource over time. The final gray distribution itself, though, is rather narrow. It turns out that this is a result of how we built the alpha function used to model competition. In this case, our alpha was chosen to reflect competitors whose niche breadth was wide, actually wider than the distribution of the resource itself. We change the result substantially when we change alpha to reflect a situation in which the breadth of a competitor's niche is narrow, specifically more narrow than the resource distribution that's also part of the model. If we change our model for competition in this way and rerun the simulation, here's what we get. We still have the phenotype distribution centered at the most abundant resource, but now there seems to be much more diversity. By way of summary, let's use the predictions arising from our simulated model to address the question posed earlier in the video. Recall, we had asked about how evolution might achieve a balance between the benefits of targeting abundant resources against the costs of exploiting what would presumably be a very popular target. We see that our simulation predicts that the modal phenotype of the derived distribution will target the most abundant resource, here at 0. The extent of the variation around this mode, however, depends on the width of each competitor's niche. When each competitor has a very broad niche, they're able to exclude a wide range of other consumers. In this case, there's little ecological opportunity, and derived phenotype distributions are predicted to be narrow. On the other hand, when competitors all have narrow niches, there's a lot more ecological opportunity that can be pursued. The prediction in this case is that derived phenotype distributions are broad. Much more phenotypic diversity occurs here. During our in-person meeting, we'll explore how to use mathematical modeling rather than simulation to derive the results we achieved here. Between now and then, I hope you get a chance to check out the simulation and maybe have a go at running it yourself. See you soon.